immune system helps to protect you from invasive diseases. However, have you heard of a case in which the body's natural cells cannot tell the difference between the foreign cells and the normal ones, causing it to mistakenly strike the normal cells? You heard it right. It's called the autoimmune disease. How does monoclonal antibodies fit the picture? Well, monoclonal antibodies are man-made antibodies cloned from a distinct white blood cell, and they function just like any normal antibodies in our immune system. They have completely revolutionized the treatment of autoimmune diseases, and various of them have been approved for use in the last 3 decades. Common sources of the manufacturing of monoclonal antibodies include using mammalian cells, such as Chinese hamster ovary cells or CHO cells. Whoa, rewind. What are CHO cells and how are they prepared before being manufactured? We will start from the very beginning.
CHO cells are cells cultured from the foreign tissue of a female Chinese hamster. Back in 1957, a researcher named Theodore decided to isolate the cells and noticed that the cells spontaneously immortalize upon culturing. Along with their advantages as they are easy to cultivate, adaptable, easy to transmit genes, and clean record in producing safe bioactive proteins, CHO cells is widely used as a stable mammalian cell line. For CHO cells to produce MAB, the genes must be first expressed in the cell, making plasmid an important component. We use plasmid as a vector to deliver genes using recombinant DNA technology. Both plasmid and CHO cells will then undergo various upstream and downstream processing, but first we'll start with the upstream processes.
This is an overview of the upstream processes of monoclonal antibodies from CHO cells. Different CHO cell lines use slightly different modified growth media with the addition of glutamine, antibiotics, and anti-clumping agents. Then, the transfected CHO cells will clone itself to form numerous copies before undergoing a screening, usually by ELISA assay, to filter out the cells that have low monoclonal antibodies activity. Once we obtain the CHO cells that for sure will produce monoclonal antibodies, we culture them in large scale. The first one that we will be talking about is the bioreactor designs that are commonly used. The pitch blade impeller bioreactor system consists of a flat blade that is set at a 45-degree angle, and the position of the blade increases the oxygen mass transfer, allowing the media to be evenly mixed via a radial and axial flow. The packed bed bioreactor system is equipped with a packed bed impeller designed to have punctured metal screens horizontally positioned in a basket. It also consists of fibrocell discs that are placed in between the metal screens to ensnare the suspension cells or create a surface for anchorage-dependent cells to adhere to. Next is the bioreactor operation mode. So how do they actually operate? There are 2 common types of cultivation, which are fat batch and batch. The fat batch process involves a nutrient-rich medium to be added to the cultivation in order to avoid depletion of nutrients. It supports large numbers of cell density and the production for a longer period of time. The batch process consists of the cells being grown in a nutrient-rich base medium that has a specific volume, wherein the entire batch is then harvested once the manufacturing process is complete. To gain high-quality monoclonal antibody yields, various parameters have to be monitored in the culture and they are listed here. However, the main parameters that are usually monitored are pH, dissolved oxygen, temperature, and osmolarity. These parameters are monitored by a bunch of sensors and are usually involved in a feedback loop to keep these parameters constant. A common medium brought for culturing CHO cells is using fetal bovine serum growth media as the base. For an alternative serum-free culture, F12 or DMEM media can be utilized. For maintaining and optimizing the culture, a supplement such as hydrolysate or choline chloride is commonly used to further improve the cell viability. Next, we'll be moving on to the downstream processing.
The downstream processes include cell harvest, purification, and polishing. Cell harvest, suspended matter such as cells, cell debris, and impurities were removed. This was done through centrifugation followed by filtration. Centrifugation is commonly done using a vertically mounted disc stack design, and additionally, when performing centrifugation, there are a few parameters that are needed to be considered, such as G-force, residence time, and discharge frequency. As for the filtration, the process is done to remove DNA from the culture broth and reduce the host cell protein to keep away the product from getting fouled. Protein A affinity chromatography is commonly used as an initial capture method in the purification of monoclonal antibodies. It involves a ligand called protein A that is immobilized in a matrix in the walls of the chromatography column. The clarified supernatant obtained from the harvest is loaded into the column, and as it passes through, monoclonal antibodies in the supernatant bind to the ligand, allowing the impurities to leave the column, and the column is then further washed before the monoclonal antibodies is eluted by glycine. In the polishing stage, there are three processes, which are ion exchange chromatography, viral clearance, and ultrafiltration and diafiltration.
There has been a high demand for MAB due to the increase in MAB market size and the further need to improve the productivity of MAB production. A continuous production of MAB has been considered as a potential improvement to the current steps of MAB production, such as the use of perfusion bioreactors in cell culture, multi-column chromatography during purification, and membrane technology in overall downstream processing. However, most of the studies revolving around these are conducted either on a laboratory scale or in silico. Despite its shortcomings, MAB nowadays are desired in treatments for autoimmune diseases which produced using CHO cells, and recombinant DNA technology through a series of fixed upstream and downstream processes. Hence, biopharmaceutical companies need to constantly design and improve the bioprocessing system of producing MAB from CHO cells to turn a continuous laboratory procedure into a large-scale production process for a potential future for autoimmune disease.
Today's video is all about monoclonal antibodies. If we look at the term monoclonal antibodies, it really means antibodies from a single clone of cells. So basically we take a cell, clone it a whole bunch of times, and then make all the clones produce antibodies, which we can then isolate and call monoclonal antibodies. If you remember from the immune system topic, antibodies are small proteins produced by our white blood cells, specifically B lymphocytes, or B cells. And their job is to help us fight disease, which they can do by binding onto foreign material called antigens. For example, on this bacteria, these molecules in the cell wall could be considered antigens, because they're small molecules that are foreign to our body. So when B cells detect these antigens, they'll produce loads of antibodies, which we can show as these little Y shapes. And as they spread out, they can bind to any bacteria that have that particular antigen. So if there was another bacteria of the same type, which had the same antigens, then the antibodies would be able to bind onto that bacteria as well. When we talk about monoclonal antibodies though, we're normally referring to ones made in a laboratory. To make them on a large scale, we need a lot of B lymphocyte clones. But unfortunately, they don't normally divide very quickly. To fix this, we have to combine them with fast-dividing tumor cells. And once the B cells and tumor cells fuse, they form something called a hybridoma, which still produces lots of antibodies, like a B lymphocyte, but also divides rapidly like a tumor cell. So by leaving the hybridoma cell to divide for a while in a petri dish, we end up with an army of hybridoma cells that all produce identical antibodies that we can then collect and purify. Another thing you need to know is that to get the B lymphocytes that produce the correct antibody in the first place, we normally inject an animal, like a mouse, with the antigen that we want our monoclonal antibody to bind to. Because the antigen is now within the mouse's immune system is going to generate a response and produce loads of B lymphocytes that are specific to that antigen. And this means that we can easily isolate those B cells and combine them with our fast-dividing tumor cells. Now, the great thing about monoclonal antibodies is that they always bind to one specific thing. So by choosing the right B lymphocyte, we can effectively create antibodies that bind to anything we want. So we can make them to bind to a particular protein or cell within our body, or a harmful pathogen or chemical. We can also attach things to the bottom of antibodies, like drugs, fluorescent proteins, or radioactive material. For example, if we had some monoclonal antibodies that were specific to an antigen on cancer cells, then we could locate and destroy the cancer by attaching drugs or radioactive material onto the monoclonal antibodies and then injecting them into the patient, where they'd find their way to the cancer cells and destroy them.